Okay. Today I will present Nowcasting US GDP using gated recurrent units. This will be a preliminary result. Okay, I don't have the full result, so I will present the preliminary initial results, and I hope to get feedback from these results. Okay. So all you know that gross domestic product is the most important economic indicator for nearly all market participants. But the problem is the quarterly gross domestic product is released with a delay. Therefore, economic actors need to infer the current state of economy by analyzing data released in a more timely and at a higher frequency data than GDP. Therefore, usually we need a framework that combines high frequency and more timely variables to nowcast gross domestic product. And in this study, we propose such a methodology based on a recurrent machine learning model called gated recurrent unit. As you know from the literature that many nowcasting methodologies has been proposed in the literature. Mainly the initial models, the bridge equations, mixed data sampling models, dynamic factor models, even Bayesian vector autoregressive models. And in our current time, the most of the central banks and investment banks focus on dynamic factor models. They use dynamic factor models as they can overcome a few problems at the same time, like ragged edge problem, mixed frequency data problem, and large scale data set problem. And dynamic factor models can solve all these models in a joint framework so that we can also compute news decomposition. So we can compare the inputs with the actual release data, the experimental data, and we can compute the news, the surprise index. But one of the problem of dynamic factor models and all other regular linear econometric models, they are linear and parametric models. But the true data generating process of macroeconomic variables is usually unknown. So a non-parametric and non-linear machine learning models may be more appropriate for nowcasting macroeconomic variables. However, for nowcasting, there are only a few studies that utilize machine learning algorithms. One of the early works conducted by Kornek and Mikol used linear quadratic discriminant analysis, decision trees, and support vector machines to nowcast the direction of French GDP by utilizing a quarterly data set, including business surveys. And they show that linear discriminant analysis outperformed other machine learning and benchmark models. In another early study, which is conducted by BAU, they utilized a quarterly data set again that contained only soft data to nowcast Euro area GDP with a random forest. They don't actually show that the random forest is the best model, but they show that if you select variables according to the importance metric of random first, then use these variables in a linear model. They provided good nowcasting accuracy. In another study, which is done by Richardson, they also adopted a quarterly large-scale dataset, including 500 domestic and international variables, to nowcast New Zealand GDP with various machine learning algorithms. They use like K-neighbor regression, boosted trees, elastic nets, lasso regression, reach, support vector machine, and neural network models. And according to their results, most of the machine learning models outperform linear models. And among these machine learning models, support vector machines and neural networks had the best performance. Up to this point, all these three models use quarter data and disregard both mixed frequency data problem and rect edge data. Okay, by disregarding the mixed frequency, they lose the information because they only use quarter data, and by disregarding the rect edge data problem, they couldn't compute the news. So, which is why dynamic factor models are so popular. They can compute also the news, the surprise part of the announcement, both the explanatory variable and GDP. In a relatively new study, Lorman and Mas use the monthly scale dataset. So they now switch the monthly dataset to Nowcast US GDP with a feed-forward artificial neural network. But for solving the rect edge data problem, they adopt a auxiliary model like bridge equations. So they use autoregressive moving average models to fill in missing values at the end of the sample, and they show that machine learning models outperforms dynamic factor models and performed as well as professional forecasters. And in one of the, again, recent studies, Soybigen and Yazgan also used the FredMD dataset. Instead of using the machine learning models, they use tree-based ensemble models. First, they utilize a dynamic factor models to reduce both the dimension of the dataset and to solve the rect edge and mixed frequency data problem. Then they feed these dynamic factor models to the machine learning models, and they show that these factor augmented machine learning models provide improvements over regular linear models. So here in this work, we will use a recurrent neural network model. Recurrent neural network models are beneficial for time series forecasting because they allows us previous outputs. They allows us to use previous outputs as inputs. So we can define a regular RNN just like this. So we have a hidden state which consists of which take input as the previous hidden state and input variables. Then we take this hidden state and take an activation function and find the dependent variable, and we can show these regular RNNs as just like this. These are one layer RNNs. We can also increase the layer of the RNNs. It is very simple. You just stack the RNNs, and the mathematical formulation just very similar, so it doesn't change that much. But there's a problem with RNNs. The most important problem is the vanishing gradient problem. So we cannot build big RNN models without coming across with vanishing gradient problem. So there are two important models proposed in the literature. One is long short-term memory, and the other is gated recurrent unit. In this study, we focus on gated recurrent unit instead of long short-term memory. There are two reasons for this. Because GRU, the gated recurrent units, needs less parameter than LSTM and computationally less expensive. So LSTM has 4 different gates and GRU has 2 gates. So you can see the mathematical equation here. So the important part is the upper part. We have 2 gates here, update and reset gates. Update gates allows us to bring information from past. So this deals with the vanishing gradient problem. And reset gates allows us to forget the current information, and we use the regular this hidden layer to update our current information. So this is our methodology. This is the initial methodology, let's say that, because you can use gated recurrent units to solve the rect edge data problem in several ways. So as a start, I use this method technique. How do I do this? So let's assume that F is my key layer GRU model. Okay. So starting from the balance part of the data set, I can iteratively predict both missing GDP and monthly explanatory variables. So let's assume that in a month, I have both missing monthly explanatory variables and I have available explanatory variables, and I have missing gross domestic product. But here there's a catch. I assume that gross domestic product can be seen as monthly. Okay. So here in the right hand side, previous month GDP, previous month missing variable. So I don't see the explanatory variable this month, but I see it last month, and available explanatory variable this month and previous month. So it's an AR1 process, something like this, or VRR1. And in the left hand side, I can get the this month GDP, monthly GDP, and this month missing or unobservable monthly explanatory variable. So I solve the rect edge problem as follows. Also, I try to solve the mixed frequency data problem by converting quarterly GDP to monthly GDP. So I am trying to solve these problems in a joint framework like this. Okay, this is not maybe the best solution for especially for the mixed frequency, but I try to solve it for this for now like this. So
you have 5 minutes.
Yes. So I use the FredMD dataset. For obtaining monthly GDP, I follow the procedure done by IHS Markit, and all variables are transformed to ensure stationarity. I don't use vintage data for now. I use PUSLA real-time data. I use expanding estimation window. I don't conduct that much hyperparameter optimization. So I just select GRU 1 layer and 2 layer with 64 neurons as first layer and second layer 32 layers. If I use dropout, I use 0.2. I use 50 epochs and run the models 50 times, then take the average of all the results. Okay, so let's look at the results. First result. First, I focus on the last financial crisis and around that time, and I have root mean square errors and mean absolute errors. You can see that nearly all my GRU models are better than dynamic factor models, and I estimate this dynamic factor model following Giovanni's methodology. Okay, Giovanni 2008. And you can see that the best model is two-layer GRU with dropout technique. Here I write with recurrent dropout. There's a different technique called with recurrent dropout, and here in this one I use both recurrent dropout and regular dropout, but recurrent dropout initially worsen the results compared to regular dropout. And here my other results, the figure, you can see that it regularly follows the GDP very well. There are some periods which I miss. Here is March 2011 and September 2011. Okay, so these are the results with dynamic factor model. But dynamic factor model can be also improved. This is just unimproved dynamic factor model. For example, I can use GDP now, which is a very well known dynamic factor model, which also use indirect nowcasting. So first it nowcast the components of GDP, then combine it. So it's a powerful dynamic factor model. Here you can see that powerful dynamic factor model, which is use an indirect nowcasting technique, outperform my model. It's unexpected because it's initial result and I don't use any hyperparameter optimization, but still I outperform the Giovanni's regular dynamic factor model. And if you see the results here, maybe until 2016, I start from 2012 because GDP now started 2011. Until 2016, I have comparable results with GDP now, but GDP now, especially with GRU, between 2016 and 2018, I have some problems during that period, and I should probably increase that part of my model. And this was my initial results. I should really improve the my models. But this is like a showcase. I show that initially it can beat the regular dynamic factor models, so it has improvements and it has a value. Also, I can use Nowcasting GDP and explanatory variables in a joint way. So what should I do in the future work? I don't write conclusion, but I will write the future work. I will use vintage data to have a better Nowcasting exercise. I will use hyperparameter optimization to improve my gated recurrent units. I will use data smoothing because in some studies I show that when you pass a filter among variables, you increase the forecasting results because noisy data, especially when you use machine learning models, can really decrease your Nowcasting accuracy or forecasting accuracy. Here, I first convert quarter GDP to monthly GDP to combine GDP into my GRU, but I try to integrate this in a more natural way, at least try to. And I can also use different techniques, that iterative procedures, to solve the rect edge data problem, and I will also experiment with these techniques. Okay, thank you for listening.